Hey, Dr. O here, and welcome to Homework Solutions for Chapter 2. Now, in this presentation is going to be like what you saw in Chapter 1, where I'm going to show you how I solve the problems for each problem, just show you the slide without any narration, and then following that, I'll actually take you through the steps and the reasons why I did what I did. So, let's get started. All right, so here's our first problem, and we're being told that we have a green light with a wavelength of 515 nanometers, and we need to figure out what the frequency of that light is. And they're even giving us a conversion factor, where 1 nanometer is equal to 10 to the negative ninth meters. So I always like to start with what we're given, and what we're given is 515 nanometers, and we're going to go ahead and convert that into meters. So we could just say 515 times 10 to the ninth meters. And we're being asked to calculate the frequency. So our job in calculating our solution, or trying to figure out our solution, is to find a way to correlate frequency and wavelength. And we have a formula for that. And here's our formula right here, where we have frequency is equal to the speed of light over the wavelength. And the value of the speed of light is 3 times 10 to the 8th meters per second. And with this information, we can plug everything in and start solving our problem. So here's our equation. Frequency is equal to the speed of light over our wavelength. And we can plug in our values, which is speed of light and our wavelength. And I always like to get rid of repeating terms. And we can see that we have meters on top and meters on the bottom. So we can just get rid of both of those. And it actually leaves us with that seconds. And the seconds is going to be on the bottom. And that's okay, because when you have seconds on the bottom in your fraction, it basically means cycles per second. So that's okay for it to be there, and we're going to work that out in just in a second. So at this point, all we have to do is the math, which means we have to divide 3 times 10 to the 8th by 515 times 10 to the negative ninth. And once we do that, we end up getting a number that looks like this. So we have 5.83 times 10 to the 14th over seconds. But we don't typically write the seconds like that. We can take that seconds out of the denominator and actually just put it beside our value as kind of like a unit by adding a -1 to that s. So our final answer is going to end up looking like this: 5.83 times 10 to the 14th s to the -1, which basically means cycles per second. Now in problem 2.2, we're given that we have a 100-watt light bulb that radiates energy at the rate of 100 joules per second. And they're basically telling us here that a watt is equal to 1 joule per second. Now, if the light that is emitted has a wavelength of 525 nanometers, they want to know how many photons per second are being emitted by this light bulb. So with all these problems, I always like to start with what I'm given. So what I'm given is that I have an energy rate of 100 joules per second. And I've also been given a wavelength of 525 nanometers, which we're going to have to get out of nanometers and convert it into meters. And we can use the same conversion factor that we used in the first problem. And that allows us to say that we have 525 times 10 to the -9 meters. All right, that's good. And we're being asked to find the number of photons per second. Now that per second is going to clue us in that seconds is going to be in the bottom of our fraction, which we'll very likely be able to convert to s to the -1. So let's just kind of keep our heads up for that. All right, so how are we going to get to that? Well, the thing that we know is that the energy in a photon is equal to Planck's constant times the speed of light divided by the light's wavelength, where Planck's constant is equal to 6.626 times 10 to the -34 joule seconds, and the speed of light is 3 times 10 to the 8th meters per second. And we know what our wavelength is because it was part of our given. So we're going to calculate that. Now the next thing we need to calculate is the number of photons per second. So we're going to take that energy rate, 100 joules per second, and we're actually going to divide it by the energy in the photon, the energy per photon. So let's get started solving this problem, and we're going to start by finding the energy per photon. So we're going to plug in all of our values, which is the Planck's constant times the speed of light divided by our wavelength. And I always like to get rid of repeating terms because it kind of leads me down the pathway of knowing if I've set everything up correctly. So what do I have? Well, I have a second on top here and then a second on the bottom there, and those will cancel. Even though they're on the same line, that second is underneath the line in that fraction, meters per second, so it gets to cancel out. We do have a meter on the bottom and a meter on the top, so we can cross those out. And it's going to leave us with joules, which is exactly what we want if we're looking for energy. So with all of our units taken care of, we do the math, and our value ends up being 3.78629 times 10 to the -19th joules. I like to leave all those decimals there because it prevents any propagation of error in prematurely rounding. All right. So what are we going to do next? Well, now we have to find the number of photons per second. So we're going to take our energy rate, which is 100 joules per second, and we're going to divide it by 3.78629 times 10 to the -19th joules. All right, well, that might not look like anything you can deal with, but if we put that second term as a fraction, that now we're starting to get somewhere. Now, I always like to take a division and turn it into a multiplication when I'm working with fractions. And in order to do that, you take your first term and you leave it as is. And then you write your multiplications, and then you take your second term and you flip it upside down. So we're going to just put the 1 on top and the energy of our photon on bottom, and we're going to now do a multiplication. Now when we do this, we can get rid of the repeating terms, which are the joules, and it leaves us with our seconds on bottom, which is going to be that second to the -1, which I already kind of warned you is what we're looking for. Because as you can see, we're looking to have that seconds right here in the bottom of this rate right there. So now we do the math, and that's going to give us 2.64111 times 10 to the 20th seconds to the -1. And if we wanted to clean this up a little bit, we could say 2.64 times 10 to the -20th s to the -1. So with this problem, I kind of looked at it with how am I going to get a value with the seconds on the bottom and really no units on top. And given everything else, I kind of let the units lead me down the pathway. Now I knew this formula, and I knew that I would end up with something in joules, and that I knew that I would have to do this calculation, the energy rate, which has the joules. So I knew that I kind of had some ideas. But it's totally reasonable that if you get a little stumped, always look at what you're given, look at what they're asking you, look at those units, and see if you can't set the problem up in order to get the units in your answer the way that you're being asked to present that answer. Now in problem 2.3, they give us 3 light colors, red, green, and blue, and they want us to put these in order of increasing value. And what values are we looking at? Well, we're looking at wavelength, frequency, and the energy per photon of each of these light each of these light colors. So how are we going to do that? Well, this requires that you have a chart, and I came across a chart that actually has all three of these values on it. So I'm not going to do any calculations because I'm okay with using a light chart or charts. I'm okay with that. So let's make sure we can use a chart correctly. So the first thing we want to do is we want to look at wavelength. And if we look at the wavelength values, those are going to be down here. So looking at this, our lowest wavelength value is going to be blue at 475 nanometers, followed by green at 510, and then finally red at 650 nanometers. Now, when we start looking at the frequency value, we might remember that the relationship between frequency and wavelength is one that's inverse. So we would expect this order to be different for frequency, and we might even expect that red would come in at the bottom of this. And indeed, if we look over here, it has the lowest frequency, 460 tetrahertz, and then green comes in at 590, followed by blue with 630. And then our last value, which is the energy of the photons down here at the bottom, shouldn't come as a surprise. That is going to basically follow the values for the frequency, and we're going to put the order as red, green, and blue. Now in problem 2.4, they want us to use the de Broglie wavelength formula. So the problem says that they're asking us what the velocity is of an electron that has the de Broglie wavelength that is approximately equal to a chemical bond, and that value is 1.2 times 10 to the negative 10 meters. So we're given this 1.2 times 10 to the negative 10th meters. That's going to be our wavelength, and they want us to figure out what the velocity is. And the solution that we're going to use to get there is the de Broglie formula, where we take the velocity and make it equal to Planck's constant over the mass of an electron times its wavelength. So you might remember Planck's constant is equal to 6.626 times 10 to the negative 34 joules seconds. But if we look at what's in the denominator of our equation, we're going to have a mass number here, and mass is measured in kilograms. So joules is actually what I would call a contrived unit, and it comes from multiplying different things together, one of which is a mass. So we can rewrite Planck's constant using a different set of values for joules, and it would be 6.626 times 10 to the negative 34 kilogram meters squared over seconds squared, and then we have to hang on to this times seconds, which came from here. So this is how we're going to rewrite Planck's constant using these values instead of the joules, because we're going to have to cancel some stuff out. Now, what's our value of m? Well, that's going to be the mass of an electron, which is 9.11 times 10 to the negative 31st kilograms. There's our kilograms right there. And we've already been given what our wavelength is, so let's plug in these values and solve the equation. So there is our formula that we're going to use, and if we plug in all of our knowns, we're going to plug in Planck's constant at the top, and we're going to put our mass of our electron down at the bottom, and we're going to multiply that by our wavelength. Now when we have all these units floating around, I always like to cross out repeating units and make sure I get left with the units that I want. Now because I'm looking for a velocity, I would expect that to be measured in meters per second. So after I get through crossing out all these different units, I should have a meter on top and a second on the bottom somewhere. So let's get started. So let's see, we have seconds here, and we have 2 seconds here, seconds squared, so we're going to get rid of one of those, but we're going to leave one of these seconds down here in our denominator. So yeah, no surprise there, right? And let's see, what else can we get rid of? Well, we've got kilograms on top, kilograms on bottom, and we have a meter on the bottom and 2 meters on top, meters squared. So we're going to leave one of those meters on the top. And when we look at what we've got left, we actually have meters on the top, seconds on the bottom, everything else crossed out, and that's exactly what we wanted. So we can rewrite this so that it looks like this, just to clean it up a little bit. So all of our values stay the same. I just got rid of the units. And at this point, we can do the math. So when we do the math, we end up with a value that looks like this. I didn't put the comma in. What is that? Like 6,061,105.01 meters per second. I don't typically like to see values like that. So we're probably going to go ahead and put this in scientific notation, which means we're going to move it over six decimals and say 10 to the 6 meters per second. So scientific notation. Let's talk about that really quickly. Scientific notation requires that in this first part, this number right here, this is actually called the mantissa, that you have one number to the left of the decimal and 2 numbers to the right. So if you have to round, go ahead and do that. I didn't really have to change much because beyond this second 6 right here, it's a 1, so I can keep that 6 as is. But that's the mantissa. This is how it should look when you're dealing with scientific notation. So we could do that. If we really want to be picky and look at how information was given to us, we were actually given a value that was only had 2 significant figures. So we could further reduce our answer down to 2 significant figures, making our final answer 6.1 times 10 to the 6 meters per second. Now problem 2.5 is asking us to come up with the quantum numbers that are associated with a specific orbital, that of the 5D orbitals. And they're also asking how many orbitals are there going to be in 5D. So we know that we're given the 5th orbital, and if we have the 5th orbital, we know that the principal number is going to be 5. And if our principal number is 5, then our L, which is our angular momentum, is always going to be 1 less than that. So that's going to be equal to 4. Now, with this information, we can bring up a chart and come up with these other values. And I'm going to go ahead and complete this chart. So when you're in the 5th orbital, you're going to have, in that orbital, you're going to have your S, your P, your D, your F, and so forth. So let's go ahead and lay those out. So you are going to have an angular momentum equal to 0, which means that your possible magnetic numbers are going to be 0, which means that we're talking about the S subshell with 1 orbital. Now our angular momentum could also be equal to 1, which now we have possible magnetic numbers of -1, 0, and +1. And that means that now we're looking at the 5p orbital, which will have 3 orbitals in it. We could also have the angular momentum of 2, and our magnetic numbers would be -2, -1, 0, +1, and +2, which means we're now looking at the d orbital with 5 orbitals in it. Our angular momentum could also be 3, and our possible values for the magnetic number would be -3, -2, -1, 0, +1, +2, and +3. That would put us in the F subshell with a total of 7 orbitals. Now you might be thinking, well, what are we going to do beyond that? Well, there isn't a 4th level to our angular momentum, and our possible magnetic values are going to be -4, -3, -2, -1, 0, +1, +2, +3, and +4. Now what orbital name do we give that? Well, once you're beyond the F, you just start with the letters of the alphabet, so we're going to go with G. And this one will have 9 orbitals. So this is how you would do the calculations following the rules for coming up with these different numbers. But our question isn't asking us about all of that. I just kind of went through the exercise to show you how it's done. Our question is asking us specifically about the d orbital. And so our answer would be that for the 5d, our quantum numbers would be n is equal to 5 because it's in the 5th principle. our L would still be equal to 2. Our possible magnetic number values are listed for you: -2, -1, 0, +1, +2, and it would have 5 orbitals. So problem 2.6 is still in the vein of the quantum numbers. And in this one, we're given a set of quantum numbers that is specific to an orbital. However, there's an error in each one of these sets. And we have to figure out what number that is and then replace it with the correct value. So let's look at our first set. So that would be set A, and our values are, our principal is 3, our angular momentum is 3, and our magnetic number that they're giving us is +2. Well, I can tell you already that this is the issue right here, because the angular momentum is always supposed to be 1 less than the principal. So there's our issue right there. And that number cannot be 3, but that number can be 2. So the correct answer would be your principal is 3, your angular momentum is 2, and then your magnetic number is +2. So that is the rest of those are adequate values. What about in set B? So with set B, here's our values. Our principal is 2, our angular momentum is 1, and our magnetic number is a -2. So what do you see? Well, our principal is 2, which means our angular momentum has to be 1, so those two are correct. So the problem then is going to be in this number, our magnetic number. Our magnetic number really can't be beyond this, positive or negative. So we're given a negative number here, but it can't be a -2, but it could be a -1. So the correct set of values should be principal is 2, angular momentum is 1, and then the spin is a -1, or maybe a +1, but here we're going to go with -1. Now what about our third set of numbers? So here we have a principal of 1, an angular momentum of 1, and a magnetic of 0. Well, this is a lot like our first problem where we had an issue with angular momentum. Angular momentum cannot be equal to principal, it has to be 1 less. So our issue is there, and if we were going to correct it, we would say that the principal is 1, angular momentum is 0, and our magnetic number is also 0. Problem 2.7 asks us to determine the wavelength of light that was absorbed when an electron from a hydrogen atom jumped from the 2nd orbital out to the 7th. So in order to make that jump, they had to take on some additional energy in the form of some light energy. So we're supposed to calculate what that wavelength was. So let's see, what were we given? Well, the one thing that we were given is that our electron went from the 2nd orbital out to the 7th. And we're supposed to calculate the wavelength, which is lambda. So how are we going to do this? Well, one thing that we need to do is we need to calculate the change in energy. And the way that we're going to do that is follow this equation right here. So that the change in energy that the electron underwent is the difference between the energy of the electron in the 7th orbital less that from the 2nd orbital. Now, how do we calculate those two energies? Well, we're going to use this formula right here, where the energy of the electron in a particular principal, which is N, is going to be equal to -2.18 times 10 to the -18 joules over that principal value squared. And we're going to do this calculation for the 7th principal, the 7th orbital, and the 2nd. All right, so once we get this change in energy, that'll tell us about the energy of the light that was emitted, or excuse me, that was absorbed when the electron made that shift. So then we can correlate that change of energy to the energy of the photon that it took in order to energize the electron to make that jump. Now, there's a caveat to this. If you looked at how this problem was solved in the worked example, this statement held true. But the deal with this value is that the energy of the photon must always be positive. So we kind of need to wait to see when we calculate the difference in the energy of the two principles, whether we get a value that can allow this relationship to work, or whether we need to go ahead and preserve the value as a positive number. So we're going to have to keep that in mind once we start working this. All right, once we figure out what the energy of the photon is, we have to find a way to correlate the energy of the photon to the wavelength of light that emitted it. And the relationship that we have for that is this formula right here, where the energy of the photon is equal to Planck's constant times the speed of light over the wavelength. But there's a little problem with leaving the formula set up like this, because the unknown value is the wavelength. So if we rearrange this a little bit, we end up saying that the wavelength will be equal to Planck's constant times the speed of light over the energy of that photon, where this is the value for Planck's constant and this is the value for the speed of light. So with all of this laid out, let's go ahead and start working the problem, and we're going to start by calculating the energy between these two orbitals. So we'll start with this formula, and we're going to calculate this value right here, the energy in this 7th orbital for a photon of light, and that's going to be negative 218 times 10 to the negative 18 joules times 1 over 7 squared. And then we're going to subtract this same calculation except for the second principle. And because this is a negative number in front, I'm going to go ahead and put all of that in brackets just to keep everything really clear. So here's, it's going to minus our negative 218 times 10 to the negative 18 joules over 2 squared. That's our second principle. Now we can clean this up a little bit and just say that we have negative 218 times 10 to the negative 18 joules over 49. 7 times 7 is 49. And we're going to subtract a negative 218 times 10 to the negative 18 joules over 4. Now at this point you might be a little bit, you might want to actually try to do something where you cancel these values out. You can't do that, because you have to take this first value, divide it by 49, and then you have to take this value and divide it by 4. And then you have to subtract the second value from the first value. So once we do all the math, we end up with an energy change of 5.0051 times 10 to the negative 19 joules. This is the amount of light that was absorbed when our electron hopped from the 2nd orbital out to the 7th. So this is basically the energy of the photon that was absorbed. Now keep in mind, I said earlier that the energy of the photon always has to be positive. So we're not going to say that the change in energy is the opposite of the energy of the photon. We're actually going to say they are the same, because the energy of our photon has to be positive. So we're going to preserve the value, and we're going to say that the energy of the photon is 5.0051 times 10 to the negative 19. So I did not bother to put the negative sign here, because the energy of the photon must be positive. So don't be tripped up on that. All right, now that we have our value, we're going to use this formula in order to calculate the wavelength of the light that was emitted. So let's go ahead and bring that up and drop in all of our known values. So we have Planck's constant. We're going to multiply that by the speed of light, and we're going to divide all of that by the energy of our photon. Now you know it's a good time to start crossing out those repeating terms. And we've got joules on the top, joules on the bottom. We've got seconds on the top, seconds on the bottom, and that's going to leave us with a meters, which is actually how we measure the wavelength. So let's go ahead and do the math. And when we do, we find out that the wavelength is equal to 3.97 times 10 to the negative 7th meters. Now you'll notice when we talk about wavelength, it's usually in nanometers. So let's go ahead and do a conversion of meters into nanometers. And in order to do that, I've created a conversion factor where we have the nanometers on top. That's the units that we're seeking. The meters on the bottom. We can get rid of our repeating units and then go ahead and do the math. And we end up with 397 nanometers for the wavelength of the light that was absorbed by the electron when it hopped from that 2nd orbital out to the 7th. And with that, we are done with this homework set. Hallelujah.